The sailings can be a very challenging topic, and there are multiple types of sailings problems that you can run into. First, a quick review just to get on the same page. What is dead reckoning? So if your ship was here and you plotted your position, this is a fix. You got that from the sun or the stars, you got that from your GPS or from piloting techniques, radar, it doesn't matter, you've got a fix. And this is your course, and you have some estimated speed. You can estimate where you're going to be, say in 30 minutes. If you're traveling at 10 knots, you'll be 5 miles down the track, in that 30 minutes kind of time. So dead reckoning is estimating where you're going to be based on course and speed. That typically works on any scale chart. So across an ocean, on a Mercator projection chart, doesn't matter. Dead reckoning is kind of universal. Another thing just to kind of get on the same page on is regarding a chart, if you wanted to go from position A to position B on a typical Mercator chart, you would be able to plot that as a straight line. So if you had this, this nautical chart here, and you wanted to go across it, you could just plot the two positions and connect them with a straight line, steer that, and everything would be fine. You would get to your destination based on the scale of the chart and the distance that is covered there. Along the way, you could dead reckon if you wanted to, but suffice to say, you'll kind of get to your destination as long as you steer an appropriate course along the way. If you wanted to plot a course kind of on a bigger area, say like across the Atlantic Ocean, there's no handy Mercator charts to do that. Instead, there are mnemonic charts, which take a portion of this ocean basin and flatten it out in such a way that you can take a straight line from point A to point B on the chart, and it turns it into what's known as a great circle route. So if you've ever taken like a long haul flight across an ocean, you'll see this curved route, and the reason for that is that's the shortest way between 2 points on a curved surface, on a sphere. So if you were to take this and rotate it and kind of look straight along it, you're just going to go over the Earth towards your destination and you're going to get there. So mnemonic charts are helpful for physically plotting a route across an ocean. They transition between straight lines and great circle routes. The real definition of a great circle is if you take the Earth and you divide it up equally into two parts. For instance, right on the equator. If you did that, the equator is a great circle. Cut it in half, you have two equal parts. Likewise, if you did it on any meridian or any line of longitude, the prime meridian or 15 degrees west or 17 degrees west, that would divide the world into two equal parts as well. So meridians or lines of longitude are great circles. The equator, which is a line of latitude, is a great circle. But all the rest of the latitude lines are not great circles. They don't cut the Earth equally in half. And in between these two, if you were to just take a random line to cut the Earth in half, that would be a great circle as well. So on the surface of the Earth, if you were traveling between 2 points, this great circle route would allow you to kind of cover the shortest distance possible on the surface. So key point here, meridians are all great circles. The equator is a great circle, but the rest of the latitude lines are not. So when we talk about the sailings, we're kind of combining all of this stuff. Dead reckoning, going from point A to point B, thinking about a spherical world, except instead of using a chart, we're calculating stuff. So you're going to use formulas, and you're going to use trigonometry, and you're going to use tables to look up information to allow you to get from point A to point B on a scale that doesn't fit on a handy Mercator chart. So if the sailings is another way to say covering large portions of the Earth's surface using dead reckoning, courses, AB, that kind of thing, there are a few different types of sailings, specifically a few different types of problems that you can run into on Coast Guard exams, or if you were to ever do this in real life. By the way, as an aside, for real life, most ECDIS, or Electronic Chart Display and Information System, and most ECS, or Electronic Charting Systems, can do all this for you. They have algorithms for you. And the interesting thing is they all kind of assume a spherical Earth, but the Earth is actually a little bit squat and flattened. And so the accuracy that you can get to is not as much as you would predict using, based on a life with Google Maps kind of thing on your phone. So the accuracy of traveling a huge distance of Earth is a little bit less than you might predict. You have to take into account that squatness of the Earth if you ever wanted to truly get pinpoint accuracy, like if you were shooting a missile or something. But anyway, that's an aside. These are the different types of sailings problems you can run into. So we're going to run through each of them just broadly. First, parallel in meridian. So if you think about the world, the equator is a parallel, and all these different lines of latitude are parallels, and longitude lines are meridians. So if you happen to be going due north or due south, you would be meridian sailing. That's interesting because no course changes are required. You just go straight north and you kind of travel up this thing. But you are actually doing a great circle, because remember that all meridians are great circles. So there's no real special math necessary for that. And the thing about latitude is that latitude is conserved. Just like if you're plotting on a Mercator scale chart, you can use the left or the right side to measure latitude, or measure distance rather. You can't use the longitude to measure distance because longitude lines converge at the poles. We'll get back to that in a little bit. So meridian sailing is just going north or south on a meridian, a constant meridian, and nothing really special is needed there. Similarly, parallel sailing is just sailing along a specific line of latitude, or a parallel. The only difference with parallel sailing, and it's a little counterintuitive, but as I mentioned, the longitude lines converge at the poles. So if you're traveling this distance, along a parallel between longitude 1 and longitude 2, that distance is going to be pretty big. But if you do the same thing up here, between longitude 1 and longitude 2, that distance is going to be pretty small. So the thing about parallel sailings, and I'll try my best on the artwork here. If this is the actual center of the Earth and we were like projecting outward, we've cut the Earth in half, and you're traveling along this line of latitude. So you're just on the surface of the Earth, right? And you're kind of covering different longitudes, right? Those are your different longitudes. Well, this is actually going to be like an arc on the surface of the Earth. So if you were doing it down here at the center of the Earth, it would be very small. On the surface of the Earth, it would be very big. And if you projected that out into space, it would be even bigger from there. So parallel sailing does require a little bit of math because it involves an angle between two longitudes, which corresponds to a distance on the surface of the Earth. At the equator, it's very big. At the poles, it's very small. So meridian sailing and parallel sailing are two pretty straightforward techniques. If you're just keeping one course, you're going along a latitude or a longitude line. Meridian sailing doesn't have too much work to it. Parallel sailing does, because the convergence of longitude lines, it really depends what parallel you're going along in order to determine the distance that you're going to cover. Plain sailing, notice the spelling. It's not like average, looking sailing. It's plain, like a flat surface. That's going to assume that the Earth can be represented by like a flat surface. So this is for areas that are not super big, but they are bigger than a Mercator projection chart, which is kind of similar. So, I'll just actually jump into it now. If you were to create a Mercator projection chart, the way that these work is imagine a little projector in the center of the Earth, and then you wrap the Earth in a cylinder. If you were to project light out from the center of the Earth and plot these points on the cylinder that's around the Earth. That's kind of how this Mercator projection chart is made. And so for Mercator projection, it's very similar to having a flat plane on the curved surface of the Earth and then representing positions on it. So if you've ever looked at, world maps where Greenland is as big as Africa, the reason is that it's a Mercator projection and it distorts things towards the poles away from the middle here. So Mercator projection is similar to like putting a plane up against a globe and then trying to measure off of it. The two techniques for sailings are similar as well. Plane sailing just deals with kind of shorter distances. Mercator sailing does larger distances, but it relies on Mercator projections. So with plane sailing, it's really just kind of like a little bit of trigonometry. So if this is your latitude number 1, and this is your destination, this would be your latitude number 2. Number 1, number 2. And this would be your longitude number 1. That's the symbol for longitude, lambda. This would be your longitude number 2, and this would be the path that you would take between them. So what you've got is you've got a distance that you can cover, and you've got a change in latitude, let's call it like L. You've got a change in longitude, let's call it like P, we'll get back to that. And then you've got an angle here. This would be your course from north over there. So you've got sides of a triangle, you've got angles, that's a 90, this is your course. So you can figure out kind of the rest. So if you know the difference in latitude and you know the difference in longitude, you should be able to calculate the distance that you have to cover, the hypotenuse of a triangle. So plane sailing is really just kind of like SOHCAHTOA of trigonometry. So sine is opposite over hypotenuse, that kind of thing. If you're trying to figure out a distance, or if you're trying to figure out a change in longitude or a change in latitude or a course, all of that is related to trigonometry. And that's how plane sailing works. The only difference with Mercator sailing is that it considers, instead of a plane on the side of the world, it's a cylinder, and it's a Mercator projection chart. So there's just a couple of little differences in how things are termed, but it's really like pretty much the same deal. Mercator projection. All right. The next one deals with what's known as middle latitude or mid-latitude sailings. This kind of combines plane sailing with parallel sailing. And so in that same situation, if this is where you're heading from A to B, you've got latitude 1, latitude 2, longitude 1, longitude 2. You've got your course, you've got your distance, but what it does instead is it assumes that you can average out these latitudes and just kind of use that average to plug into a little bit of a different formula to kind of estimate your distance and your course in a cleaner manner. So middle latitude sailing averages the latitudes. That's one technique of doing it, whereas Mercator kind of does the difference of latitudes. Some of this can become tricky if you cross a hemisphere, like from the north to the south, but big picture, plane sailing, Mercator sailing, it's trigonometry related. Middle latitude kind of combines like parallel sailing with Mercator sailing, just a different process, a different formula that you might need to use. And again, by the way, all these formulas are in Bowditch. You don't have to memorize really anything. Traverse sailing is just doing all of this same stuff with multiple course changes. So instead of crossing an ocean, if you were having to navigate through channels and different areas like that, you could use traverse sailing, and you look things up in the traverse tables kind of thing. And then finally, great circle sailing. This would be very large distances on Earth, and it would allow you to kind of not just do the course and the distance. If this would be your course, this would be your distance. It would allow you to calculate any point along the way. It would allow you to calculate, say, the the vertex, which is the highest point on a given great circle, the most poleward route. So great circle, is a little bit of a different project, but it allows a few different calculations, and the way the Coast Guard problems will come at you is a little bit weird as well. So great circle sailing is just one technique of sailings for really long distances, and there's a few other nuances to it along the way. All right, so those are the main types of sailings problems we can run into. Just as an overview, you'll be able to dive into each one as necessary for the Coast Guard exam. Okay, next we need to talk about a bit of terminology for sailings problems. And so this is mostly going to be related to mercator sailings or middle latitude sailings, but the terms are helpful for all types of sailings. So imagine kind of a couple of cases where you've got position A and position B. You want to go between them. We want to know the course or the distance or the change in latitude, that kind of thing. Most of these types of problems are going to rely on creating a right triangle between the two positions. And I'm showing you two varieties, but you could also be heading southwest or southeast as well, so just keep that in mind. Terminology, number one, latitude has kind of two positions, your original latitude and your final latitude. So no matter what course you're taking, unless you're parallel sailing, you're going to change latitudes. That's also known as the difference in latitude. Difference in latitude. So sometimes that term comes up. That's technically an arc. So if you were to kind of come from the middle of the Earth and project out, the arc difference from latitude 1 to latitude 2 is what we're actually after. It's a number of degrees, so it would be an angle or an arc. Another term for this is L. L would be kind of the same thing, but traditionally it's more noted in nautical miles. Now for latitude, changes in arc and changes in nautical miles are the same because latitude is conserved on a sphere. So difference in latitude, L, pretty much the same. Usually you consider one as an angle or a number of degrees, the other as a number of nautical miles or a number of minutes, as the case may be. So latitude 1, latitude 2, the difference, and then L is your key word there. Longitude, similar vibe, but different structure. Lambda is the symbol for longitude, so lambda 1 and lambda 2. Those are your two different longitude lines. The difference between them would be delo, or difference in longitude. The difference in longitude is also an arc, just like the difference in latitude. It's a number of degrees difference. 15 degrees in 26 minutes, 75 degrees in 13 minutes. That's the difference in longitude. All you have to do is subtract longitude 1 from longitude 2, or vice versa in a different hemisphere, and you'll have delo. The other term for that, similar to this, is P, which is known as departure. And that's going to relate to a number of nautical miles. So you can convert that arc into a number of nautical miles. However, for longitude, remember that as longitude changes, it converges towards the pole. So a difference in 10 degrees here would be different number of nautical miles than a difference of 10 degrees up there. And so departure and little l have the same vibe, but they are different things. So departure is going to be a number of nautical miles based on where you are, where your latitude is. Whereas L is conserved no matter what your latitude is. And this comes into play with middle latitude sailings because we're picking an average latitude and we're just saying, okay, that's going to be our average latitude. What's the departure based on that? And then that goes into the calculations from there. So latitude 1, latitude 2, longitude 1, longitude 2. This is distance. That's just a number of nautical miles. And that's what we use as our little navigation world to estimate speed, distance, and time, or to kind of give an ETA for an arrival kind of thing. And that's what we want to know as navigators. Nobody's going to care about departure or difference in latitude. We want to know the distance that we're going to cover. And so that's where that pops in. And notice that's the hypotenuse of this triangle. Same deal over here, doesn't matter. So all of this kind of repeats on this triangle over here. The distance, the difference in latitude, they are kind of absolute values in this case. Where things go a little different, and it can be confusing, is this angle right here, which is your course. So as mariners, we want to know the distance and the course. So if this is north and this is our destination, that would be our course. Say it's 45 degrees true. Well, if we head off on course 45 degrees true at whatever distance, we're going to make it from A to B. But look at these triangles. They are the same, are they not? Or at least to my artistic ability. So this would also be 45 degrees, but we're not going to lay in a track of 45 degrees. We won't get to position B. Instead, we'll go off that way. So our maritime nomenclature makes our degrees from 0 to 360. So if you go on course 045, that means something specific. But mathematically, this triangle is just the same as this triangle flipped around. So you can't put in, different numbers. 45 angle is a 45 angle. So this is where we come into what's known as course angle notation. So C is going to be the course angle. And this is what gets thrown into your calculator. This is what gets put into these triangles, whether you're going northwest, southeast, southwest, or northeast. That's the number you throw into your calculator to get results from formulas. What we want to know as mariners is actually going to be something known as CN, or course. That's the number you would tell the helmsperson to steer in order to get to a specific destination. Good news for you, if you want to do a little experiment, take your scientific calculator and put in 45, let's say. Take the sine of it and you'll get some number. Put in the opposite of 45, like 315. Take the sine of it, you'll get the same number, just with a negative sign. So if you can reason out where your ship is headed logically, and you throw the wrong number into the calculator, you might just have a negative sign mixed up. And usually on a Coast Guard exam, you can sort out the right answer by logicking out what you're doing. However, it is much better to get this course angle notation thing down so that you put the correct number in the calculator and then you have no ambiguity about what you're typing into the calculator. All right, so there is a little bit of a formula that I'll show you here in a little bit, but just note these main key terms. DLAT, L, DLO, P for departure, the differences in latitude and longitude, the distance, and the course angle. A couple other ones to throw in there. You could take the middle latitude, as I kind of described with this middle latitude stuff. That would just be the arithmetic middle point of these two latitudes. You could also take the mean latitude, not like the angry latitude, but the average latitude. And that's similar to mid-latitude, but remember on a sphere, our notation of latitude is a little bit different because we have north hemisphere and south hemisphere. So the mean latitude is if you're in the same hemisphere. The middle latitude is the same as the mean hemisphere, but it goes across kind of both hemispheres if you need to. Okay, so back to this course angle thing, now that we can erase the board. So this course angle stuff can be a little bit tricky. Two ways that I would recommend thinking about it. Number one is if you can logic out where you're headed, like if the Coast Guard clearly tells you you're heading northeast or southeast or southwest, you may be able to just know the right number to put into your calculator when the time comes. And again, remember that if you put in a certain angle and you're off on the course angle, it's just going to give you a negative sign, perhaps. So you can probably logic out the right answer. A more reliable way, though, is to understand course angle notation and do the right thing each time. So you could memorize, or learn, I guess would be a better way to say it, kind of the 4 quadrants. Let's take as an example, all of our geometry is going to involve a 30-degree angle. No matter what triangle we're looking at, it could be a triangle up here, flipped on its side and rotated, or kind of that way. It's still going to be the same 30-degree kind of sailings issue that we're looking at, given the difference in latitudes, the difference in longitudes, the departure, etc. So in the northeast hemisphere, if you were heading this way and your course angle was 30 degrees, it's going to be the same as your traditional maritime course, 030 degrees true. So 30 degrees true is going to be the same. And just as a reminder, like C is the math thing, CN is your course angle. Or your course rather, sorry. This is your angle. So CN would be like the real thing that you tell a helmsperson. So in this case, C equals CN. No change if you're heading to the northeast. You could also name this angle a specific way. You could name it north for the reference direction, 30 degrees for the angle, and then east for how it's modified. North 30 degrees east is another way to think about this if you like it. Same thing, if we had that same triangle, 30 degrees there, and we were in the southeast hemisphere, this would be south 30 degrees east. South for the reference direction, 30 degrees for the angle, right, the course angle, and then east for the deflection for our little triangle. Took that triangle, just flipped it over kind of thing. So the math is going to be the same. 30 is going to be the number that goes into it, but that's not our course. If we headed 030, we would be going that way. Instead, we're heading like a different number, 150 in essence. So in this case, think about 180 down here. In this case, your course is going to equal 180 minus your course angle, minus the mathematical angle. So 150 in this case. So put in 30 and take the sine or the cosine of it. Put in 150, take the sine or cosine of it. You'll see they're related. They're either inverses of each other or they're negatives of each other. It's all just the same triangle flipped around. All right, if you're heading in this direction, to the southwest, right? Southwest. This same angle, 30 degrees, it would be south 30 degrees west. You're putting 30 into the calculator, but it's actually going to be 210 degrees true, right? 180 plus C equals the CN. The actual course. CN is what you tell the helmsperson. C is what you put into a calculator. And then finally, same thing. Same triangle, just rotated 30 degrees. You know, you're doing all this same stuff. This is north. We'll also call it 360 for our math purposes. And so this would be north 30 degrees west. North for the reference direction, 30 degrees for the angle of the triangle that you're doing, and then west for the deflection of it. So CN would equal 360 minus course angle, or 330 in this case. All right, so this will make a lot more sense once we start doing problems, but in this kind of big introduction, I know it's a long introduction to the sailings, but we've talked about kind of what the sailings is, what it means, and so my takeaway is that it's just doing dead reckoning and going from A to B on a large portion of the Earth. You can do it a few different ways. We talked about parallel sailing, mercator sailing, plain sailing, Meridian, mid-latitude, and great circle sailing, among others. And then finally, there's some key definitions. Departure, latitude, difference in latitude, difference in longitude, course and course angle, all of this stuff right here, and then distance. Those are the key things that you'll end up putting into the formulae when we're doing all of the sailings. Regarding the course angle specifically, which I think is probably the hardest concept, you can do two things. You can logic out where you're headed, if you're headed in this direction or this direction, and you get a negative sign on your formula, or maybe it's the inverse of a trig function, you can pretty much get to the right answer with enough experience. If it's new to you, I would recommend memorizing or learning something like this. Think about what quadrant you're in, name the angle appropriately, remember that they're just triangles flipped around, it's all the same math, and then these four formulae will be something that you can help remember. Bowditch is available to you on Coast Guard exams, and there's a whole section about the sailings. It defines the different types, it talks about course angle. It's not a very detailed discussion, so it's worth having some of it up in your head, but do remember that you can always refresh yourself on the exams in Bowditch. So next we're going to move on to take a look at some of the different types of sailings problems you can run into, but I hope this introduction is helpful to frame it for you.